Alright, we just came off of electricity and electrostatics, so now we're going to move right into circuits. Okay, so since we're moving on to circuits, we're primarily going to remember that we have our power source, which is actually our voltage. We have some sort of load or resistance that we have to have in a circuit, which is going to be some type of light, resistors, anything that's going to use the electron energy. Then we have a current, which is always going to go out of the positive of the battery and into the negative. And remember, that's the conventional flow of current. And the reason that it goes that way is because of the positive test charge. And that was all determined on that positive test charge. And if you remember in our electric fields, we talked about a positive charge moving away from a positive charge and a negative charge, and around a negative charge, the electric field moving into it. So even though I will tell you, really, the current flows the opposite direction because of the positive test charge, we really do it that way instead. Okay? So, talking about circuits, some more information. 4 devices are required, like I said, when we study Ohm's law. Remember, Ohm's law was our formula, I equals V over R, which I like to rearrange and have V equals IR instead. But you have to have a battery. You can have a voltmeter, which measures volts. You should write that down. And you can have an ammeter, which measures amps, which you should write that down as well, and some sort of resistance. The ammeter and the voltmeter, the ammeter measures current, the voltmeter measures resistance. We had a multimeter in class, and we just turned it to measure what we wanted it to. All right? So the thing to remember is that you also need to write down your ammeter always needs to be hooked up in series. That means it has to be a part of the circuit. So we had to break the circuit and put the ammeter in it somehow to read the current. The voltmeter, on the other hand, doesn't have to be a part of the circuit, so the voltmeter will always be hooked up in parallel. Again, you should write those two things down. The ammeter has to be hooked up in series, and the voltmeter has to be hooked up in parallel. So ammeters measure current through the battery, the filament, and itself. So that's why it has to be hooked up in series. The voltmeter measures the voltage across the battery or across the resistor, but it's always across something, and so that means it's hooked up in parallel. All right? Now, the following symbols are going to be used when we talk about schematics for electric circuits. And what you need to remember is we won't use all of these, but this is probably somewhere where we need to pause and you need to write some things down. Any type of wires are just going to be straight lines, so you should write that's done as a conductor. Anytime you have a break in that, that's going to be a switch. A resistor is just going to be a wavy line of the wire because it's going to actually have to use more electron energy to move up and down instead of in a straight line. Then you should write down what an ammeter is, and it's just a circle with an A in it, and a voltmeter, which is just a circle with a V in it. And then you should write down a battery. Okay, a battery is a long line and a short line. This shows it as a square and a long line, but it's really just two parallel lines, one long, one short. And then you should write down what a light bulb looks like, which is really just a special resistor. It's the same resistor symbol, just with a circle around it. But you should pause and make sure you get all those in your notes for schematics on electric circuits. All right. Now, we've already dealt with resistors before, and we're going to deal with those in 2 other labs later in this unit in class. But really, the bands tell you the coloring, and they also tell you how much tolerance it will have, which means how much difference it can be off when you read it. So it can be either a plus or a minus off of the actual reading. So, but I color-coded those for you in the lab, and they're just in the baggie that way. So it's just telling you that you can do it that way. So why can a bird stand on a high voltage wire and not get shocked? Okay, we're going to talk a little bit about electricity here for a minute. And that's because the fact that there is no potential difference between his feet. The path of least resistance right here is through the wire, and so there won't be a voltage drop from one foot to the other. And if there's not a voltage change, then he won't get shocked. Now, if I have these two birds though, one of them has a lamp in between its feet, the other does not. Now, once this circuit gets closed, because right now the switch is open, if we were to close that so that it could go, and the bird right here would actually get shocked because that lamp would use some of the voltage. So the voltage that he had at this foot would not be the same voltage at that foot. So they would be different from each other. And since those voltages would be different, they would end up getting shocked. Okay, but just that one. This one, the voltage here would be the same voltage as here. And so since those are the same, he wouldn't get shocked. So it has to do with the fact of whether there's a potential difference between their feet or not. So let's talk a little bit about electrical safety, because in my opinion this is a big deal, and I always like to have this discussion with my classes. Most of you have seen a 3-prong plug like this, and that's known as the ground plug. Now the ground plug is there because of the fact that it's connected to an appliance, and the wall jack will receive the ground plug, and it's actually then connected to the ground. So any charge that leaks onto the appliance will drain into the ground and not into you. And that's really important because, like for an example with a dryer, if all of those electrons and all that friction had electron buildup on the actual dryer, when you touched it, you would be powerful resistance, and so you would get shocked. But because there's a ground wire and a 3-prong plug, whereas this is showing it doesn't have a 3-prong plug, since there is on all of those types of appliances, then you don't get shocked. So it's really important, especially with power tools. If for some reason the ground plug breaks off, you need to find a way to replace it. Do not use tools that don't have their ground plug if they're designed to have one. So, a couple of things you might want to know about electricity. If you get shocked with 1 milliamp of electricity, it's just really kind of a tingling sensation. And if you do 10 milliamps, this will cause your nerves and your muscles to overload. Typically, what happens with this is tasers, that's what I was looking for. Tasers are anywhere around 10 to 20 milliamps most of the time. And so when you watch the TV shows and somebody gets tased, you know, everything locks up and they shake and everything. That's because of the fact of how much current's running through their body. 200 milliamps is typically where they start a heart defibrillator. It can be fatal depending on how it's administered and if your heart is already beating and things like that. But they'll start with a charge of about 200 milliamps and go up from there. 500 to 1,000 milliamps won't, again, it could be potentially fatal, but again, your heart will restart with those types of milliamps. So when you see hospital shows and they say charge and clear, that's what they're meaning, is they're charging it so it holds a charge that can pass a current that's going to be anywhere from 200 to 1,000 milliamps. Now, 1,000 milliamps is also an amp. And an amp or more will actually burn you alive. So that's a big deal. Their electrical burns are serious. My son, one time, he actually decided he was going to test electricity in his room. We didn't realize he was doing that. But he was smart enough to hold an insulator, but he did stick something into the plug. That is a great way to get seriously hurt. So because you've got a large amount of electricity passing through your body. So don't do that. Bad things happen. We knew a kid one time that they were playing Bet You Can't, and they ran a tree house. So they bet him that he couldn't grab a hold of the power line that was right outside the treehouse. Unfortunately, when he did grab it, there was a voltage, there was a potential difference between his hands because he didn't realize that. And it actually, there was enough current running through his body that it locked him onto that. And then that current going through his body caused severe burns. His friends couldn't touch him because then it would have gone through them because they weren't grounded in any way. So they had to get a piece of wood and literally hit his arms to get him off of the power line. He was really badly hurt, and it took him, he didn't die, luckily, but he was really badly hurt, and he was burnt over 3/4 of his body. So electricity is not something to play with, okay? So don't dare your friends to play with electricity or things like that, or do things that y'all know it's going to hurt each other, because y'all are important. Don't get hurt, okay? So, as more and more appliances are added to a circuit in parallel, and we'll talk about this a little bit later too, the resistance will decrease, and so the current will actually increase if you look at Ohm's law. And too much current can result in an overload or a possible fire. So what happens is we install things like fuses and circuit breakers. Okay, fuses and circuit breakers are used to prevent overloads. And what they do is they limit the amount of current that can flow through the circuit. And what happens is there's a little strip inside of here, inside this circuit breaker, this actual fuse right here. And if too much current goes through this metal, it'll actually burn it up. And once it burns up, it breaks. And any break in a circuit is going to cause it to where the current can't flow. So you can replace them. It's real easy. I do that in your multimeters. So if too much current runs through it, if you don't hook it up properly, then it just burns out the little piece of metal. And so if you work on radios or anything in your cars, your stereos, your systems, they have fuses a lot of times as well. So do lights. Christmas tree lights and things like that have fuses sometimes also. Houses use circuit breakers instead of fuses, so these don't have to be replaced. But what they have is something called a bimetallic strip. And the bimetallic strip actually heats up, and one side heats up faster than the other. So this is actually brass and steel. The brass is going to expand more than the steel will when it heats up. So it'll actually bend over. So as it expands, it bends over into that little location right there. And as it bends over, then that spring is going to pop. And so what'll happen is it'll flip your circuit breaker. So that's what happens like over at the pool when the swimmers, the girls especially, I will say swimmers, it's the girls' bathroom, when they plug in too many hair dryers and straighteners, then they'll flip a circuit breaker. And when they flip a circuit breaker, that nothing will work until they reset it. So you just can go and push it. So go look at your circuit breaker outside your house sometime. It's typically either outside or in your garage, but just go look at it, and they're just switches, and you can tell whether they're on or off. All right? All right, so that's all I've got for today. It's not the end of the class period. You guys should be working on some classwork on open and closed circuits, and you're really just going to be looking at if the current can make it from the battery, the positive end of the battery, back to the battery. When certain switches are closed, then certain devices will work. Remember, you can't go backwards in current. You can only go out of the positive and out of the positive and into the negative. All right, be good. See you soon.